So one more thing I wanted to mention is that when we actually do this experiment, we're going to need to use something different, right? This time, for all the previous experiments, you did all the data acquisition work, right? So you would, so in the pendulum experiment, right, the pendulum would swing a period. You would sort of manually start and stop the timer. You would read and write down what number the timer gave you, and do the hex to decimal conversion. And then you would manually press a button to clear the counter and get ready for the next run. Well, that's going to be hard to do with this experiment, right? Because we're gonna have a situation where we have pulleys like this, right? Pulley rotates, it's blocked, going through a third of a rotation. We measure that, but then we want to get ready for the next measurement right away because this thing is going to be rotating fairly quickly. Even if I just spin it up with my finger right here. And so instead of using our 7-segment display, what we're going to do this time is going to use a computer interface. And I'll show you that. Actually, let me show you what I have. So for the lab video on Thursday, I'm going to show you this in more detail. I don't know how well you can see this here, but right, you can see that I've got this board, which is my measuring circuit, and instead of the 7-segment display, oh my gosh, I can't reach around. Okay, I have here this National Instruments interface. It's a thing that I don't know if you can see, but if I turn this around on its side, you can kind of see how there's a right where my finger is. There's a little there's a port that for a USB cable whereby I can connect that to a computer. So let me go put this down before I drop it. So the interface is going to do a couple of things. So we're going to have to kind of black box the interface, unfortunately. Its inner workings will be a little bit mysterious, but it's really doing 3 basic things. It, number 1, needs to read data from our counters. So instead of just displaying the data with the 7-segment displays, we'll just read it with the interface. It's also going to need to do what we used to have to do manually. Namely, it's going to have to clear the counters. I'll show you how that works in a second. And it's also going to have to do what we want, which is take the data it collects, send it to a PC, and then the PC will save the received data to a file. So in a second, I'll go and cut to my laptop where I can show you a diagram of this and how it works. So the computer program that controls this interface was written by a student a bunch of years ago. It's a little bit clunky. It's some C code which uses some libraries from National Instruments. It works. That said, this is maybe a challenge to some of you in case you're ever interested. There's no reason we couldn't do this using some sort of open source hardware like an Arduino or a Raspberry Pi. So maybe something that maybe one of you would be interested in at some point in the future, maybe as an X99 project, it'd be kind of cool to sort of update the data acquisition for this experiment, at least in my opinion. So we'll cut to my computer now. I'll show you how the final circuit diagram and interface works. And then when we come back on Thursday, we'll go through the circuit in detail and then start to think about what measurements we might be able to take. So here's the diagram for our circuit as we described. As you're very familiar with by now, we have down here our photo gate. And as we described, we want to take that photogate signal labeled C here and feed that into our divide by 2 circuit, which we've made with a flip-flop, just as we had talked about earlier in the term. For reasons we're going to see, we're going to want to be able to clear the flip-flop with a push button, so we've got that there. Thereafter, the next part is fairly straightforward. As usual, we're going to feed the output here of our flip-flop into an AND gate along with our reference clock. And then this goes to our cascaded binary counter, so we have 12 bits as usual. So the new thing this time is that we're going to take the counter outputs, and instead of feeding them right to a 7-segment display, we're going to go to this computer interface, and I'll have more to say about that in just a second. So here's a timing diagram of the completed circuit. So as we talked about before, we've got a flip-flop clear button so that we can control the state of the flip-flop's output. We have our photogate here, which is high when we are blocking light. Our reference clock. And so notice that once, after the clear of the flip-flop, and the clear, if you recall, is an active low, is denoted by this bubble here, so it goes low to assert clear. But after we stop asserting clear, the flip-flop starts doing divide by 2 as we expect. So we have we have the output here being toggling on every rising edge of the photogate signal. And then once again, ANDing this signal with our reference clock gives us pulses that we know how to count. So the interesting thing here, is what the computer interface is doing. And so there's sort of 2 more signals. So it turns out that the computer is programmed to count, these pulses, but then there's no counting going on when the flip-flop is low, When this flip-flop output is low, the output of our AND gate is also low. The key is that the computer is also, the interface is also connected to the output of our flip-flop here. So this is that data ready to computer signal. So when this flip-flop output goes low, the computer knows that data reading can commence. So it reads the data and transmits it to the PC, which is this signal down here. And then the interface sends a signal to clear all the counters. That's the signal F to all the clears of the counters from our interface and our computer. So what this means ultimately for us is that the way the circuit works, we measure the time it takes for the pulley wheel to rotate 1/3 of a rotation, but then it takes another third of a rotation to actually read that data. So we get one data point here, but then the next data point actually comes after the pulley makes 2/3 of a rotation, and just continues on and on until the program stops, and the computer program is set up to stop after 4 seconds.